Hi, and welcome to this section of the Calculus 3 tutor. And in this section, and actually in this section and the next several sections, we're going to tackle the topic of line integrals. And I split this topic up into several little sections because I think it'll flow a little bit better that way. So line integrals is what we're going to talk about here, and the introduction to it anyway. And we're going to do several problems that talk about that. So what is a line integral, okay? What it is just remember back from Calculus 1 when you were first introduced to the concept of an integral. Okay, you had an f of x, you integrated from a to b, and you integrated that function, and you integrated it along x because it was a function of x. It's the only direction you could really integrate. It was a function of one variable, so you could only integrate along that variable. Okay. Now we started doing the double integrals and the triple integrals, but those were all integrals really over a volume, or at least the triple integrals were over a volume, and the double integrals were actually over sort of a volume too, defined from the xy plane up to the function. So those are sort of three-dimensional integrals, so to speak, integrating a function over a region, over a volume, or over an area, or something like this. Okay, what a line integral is let's say you have a function here it could be a three-dimensional function, a function of three variables sitting out in front of us here between me and you, okay? And you have an XYZ system kind of superimposed grid right here in the room. Well, you could obviously integrate along X, okay? You can integrate that function along Y, you can integrate it along Z, but what if I didn't want to integrate any one of those directions? What if I wanted to integrate in any arbitrary path I wanted to? Maybe I don't even want to integrate along a line per se. Maybe I want to integrate along some sort of curved path. Okay, I can do that with a line integral. Okay, so just to draw the analogy, in one variable f of x, you always integrated from a to b because that's the only direction you could go. But now that we're starting to talk about all these three-dimensional functions that go in x, y, and z, then you may not want to integrate in a linear fashion from a to b along x and y, or along the x direction, or along the y direction. You may want to start from here and trace a little path down from a starting point to an ending point and kind of sum up the little values of that function along that point, okay? Along that path, okay? So that's called a line integral. Now, it is called a line integral. You don't actually have to integrate in lines. You can integrate along any path you want. It could be a little curved path. It could be a little wiggly path from A to B, or whatever you want to do. So that's what we're going to talk about here. It's not a big deal. I'm going to show you the general formula for what you're going to end up doing, and then we're going to apply it to some problems. The first thing you need to do when you're dealing with a line integral, you need to define your path, okay? You need to figure out how you're going to express this path that goes from point A to point B and maybe has some squiggly journey along the way, and we're going to do that by way of what we learned in Calculus 2, which is parameterizing an equation, okay? Using a parametric equation basically is what it is. That's how we're going to describe the path that we're taking, which is basically a vector. It's basically a vector. The tip of a vector is what we're going to use to describe that. So first, let's just move on and say, which we already really said, we can integrate a three-dimensional function along any path in space. We know we can do this. The first thing we need to do is define the path that we want to take, and we're going to define that path by way of a vector. Okay, it's a function of t. I'll tell you why we're doing that in a second, but what we're going to say is it's going to have an x of t in the I direction, a y of t in the j direction, and a z of t in the k direction. Okay, so this should look familiar to you, or somewhat familiar to you, from Calculus 2. This is a parametric equation. Okay, t is called the parameter. I like to think of t as time. That helps me. So if I start time off at 0 and then go 1 second, 2 seconds, 3 seconds, these little functions that are here in front of x, y, and z, they're going to change. They're going to change the components of this vector. And what you're really going to have here is at t1, you're going to have the vector pointing here, and at t, 5, you're going to have it pointing here. And basically, anywhere in between points A and B, by choosing these values accordingly, as time marches on, you can have that path go anywhere you want. And so since this function that we're integrating here is permeating space here, it's everywhere, we can sum that function up and integrate it basically over any path we want by choosing this parametric equation to fit the path that we want. Okay? So it's a parametric equation. Every component is a function of t. I like to call it time. And so what we usually say then is t goes from A to B. So you could say t would be going from 0 to 10 seconds or 1 second to 5 seconds or whatever. As long as you pick it properly, it doesn't really matter what t is, as long as it traces the path that you particularly want. Okay?